Here is another video on MSC Nastran Design Optimization. We're going to walk through the process of how to impose a design constraint on constraint forces if you're performing a frequency response analysis. In this video, I'll be working with the same 1 degree of freedom system. Basically, I have a spring fixed on one end, and there's a point mass at the other end. We have frequency dependent loading on the mass, so you can imagine this thing is going to oscillate. During the oscillation, we will have reaction forces induced at the constraint, but I want to make sure that the constraint, or the constraint force doesn't go beyond a certain level. Here in orange is my initial design, or rather the frequency results for the constraint force. You can see that at 3 Hertz, we have a constraint force of 900 newtons at the root. Here in blue is my final design after the optimization. The goal at the end of the video is to find a value for the spring stiffness K that will produce this new frequency response curve for the constraint forces. So here, feel free to pause the video and take a look at the description of the model. If you want me to contact you, sit down with you, walk you step by step on how to perform an optimization example of your own, feel free to reach out to me at this email address and we can definitely have that discussion. And now let's go ahead and discuss the problem statement. We're minimizing the cost of the spring, we're varying the stiffness of the spring, and as for design constraint, we're going to say that for all the forcing frequencies, we want to make sure that at each forcing frequency, the constraint force is no more than 700 newtons. So now let's go ahead and jump into the web app and walk you through the process of doing that. So let's click on constraints and switch the analysis type to direct frequency response. Scroll through the list. Alternatively, you can just filter the list for force. And here you have 2 forces available. Single point constraint force is the force at your support, your constraint, if you will. Click on the plus icon one time, and this produces your design constraint in the next table. This is where you can configure your design constraint. For SPC force component, this would be the same components that you would use for displacement. So I know that the orientation system is such that if you go in the vertical direction, that is my X direction. So that would be a force component of 1. If the spring was going in the Y direction, I would use a component of 2. But here I'm using 1. My grid ID, it's very important that we know that grid or node 1 is here and node 2 is at the mass. And the stiffness is between node 1 and 2. We want the constraint force at node 1, so we will type in a value of 1 here. And our upper bound is, I believe, 700 newtons. Let me make sure I have that correct here. 700 newtons. So we'll type in 700 here. And then this box. I recommend watching my previous video on how to impose a design constraint on frequency response displacements. In that video, described what the significance of using min is, max, RSS, RSQ, or SSQ, sorry, and average. I also discuss what blank means, and here I'll take a few moments to discuss what that actually means. If I leave the box blank, this will then impose a constraint for each forcing frequency along your results. So let me go ahead and copy these new statements since I've already configured my constraint on the constraint force. And let me copy those to my design model. This design model is already complete with my design variable, design objective statements, and now it has statements for the design constraint. What I will do next is I will start Nastran and perform the optimization on that design model. Inside of the folder are all the files of the optimization. Let me open the F06 file and make sure that I have a successful message here. Let me look at the results. So our objective again was the price of the spring. Our variables were the spring constants. And now these look in line with what I plan to get. So let's go ahead and discuss the results. Here in orange is my original frequency response curve for the force at the constraint, node 1. In orange, I can see that at forcing frequency of 3 Hz at a maximum value of 900 newtons. After we imposed our design constraint, MSC Nastran found that the new stiffness needed to honor the design constraint was a value of 2071 newtons per meter. And here in blue is the new frequency response result. We can see that at each forcing frequency, it is under the limit of 700 newtons. And you can see that the final forcing frequency, the magnitude of the constraint force, is 700 newtons. So you can think of this point as actually dictating the stiffness of the spring. At this stiffness, all of the points were satisfied, but this was the one that was being exceeded, violated the most. So this was governing the optimization, if you will. So that's how you impose a design constraint on constraint forces. If there are any questions regarding this, definitely feel free to drop me a comment in the video or in the comment section below. If you want access to this web app that makes performing examples for optimization really simple, feel free to contact me at this email address and I'll definitely get back to you. With that, thank you for watching.